Hello, my name is Kevin and I'm making up lab number 3, which is Gaussian beam imaging systems. And the whole point of this lab is to create a focus spot size from the Heaney laser, which is 1/10 of the focus spot size that we got back in lab 2. In order to do that, instead of imaging the Heaney laser directly, we're going to create a Keplerian beam expander. Let me show you how that works. Alright, so in order to have a focus spot size that's 1/10 of the size of just focusing the laser beam directly, we need to expand the beam to 10 times its normal size. And we'll do that using a Keplerian beam expander, which in this case consists of a microscope objective and a collimation lens. And the ratio of the focal length of the two determines the expansion ratio, so we need a factor of 10 increase. So we're going to use a microscope with a numerical aperture of 0.04, followed by a collimation lens with a focal length of something greater than 62.5. In this case, we'll just use a 250 millimeter focal length achromat. And in the middle of the two, of course, we'll use a spatial filter of 25 microns, and that allows the most amount of light to pass while only taking while cleaning up the beam in the meantime. Okay, so the setup here starts with the Heaney laser, which is aligned with the rail using the same method as the previous lab by using a pinhole, and then we focus it using the microscope objective onto the spatial filter, which then cleans up the beam and sends it into the collimation lens, and then we can test the collimation using a shear plate. So in this case, the reference line is aligned with the rail, and if it's perfectly collimated, then the interference lines should also be parallel to the reference line. As I defocus the collimation lens a little bit here, you can see that the lines shift relative to the reference line, which means that it's slightly out of focus, and the wavefront going into the shear plate is either slightly converging or diverging. So I'm going to put it back to parallel with the reference line here, which means that we're very well collimated. So I tried this with both the 1-inch aperture shear plate and the 2-inch aperture shear plate, and I found that the larger aperture, the 2-inch, actually had much better sensitivity. Okay, so after we determined that we had a collimated beam, after it was expanded, we then used an imaging lens, the same one as in the last lab. It was a focal length of 200 millimeters to focus the spot. You can see it somewhere in here. We then want to determine what the size of the focus spot was, so we used the same method that we used in the last lab, using a knife edge at 2 different locations to figure out what the beam waist was and what its location was. It was a little trickier in this lab because the focus spot is so close to the detector, and you can't overfill the detector or else you get inaccurate data. So I used the method of placing the knife inside of focus for 2 different locations, and from that information you can still figure out where the actual beam focal point is and how big the focus spot is. In the last lab we used both methods, where you take measurements both inside focus or both outside of focus, and then there's another method where you can take one measurement inside focus and then another one outside, but I'm going to use the method because it's more practical in this situation to take measurements both inside focus. Okay. So this is the results from one of the knife edge measurements I took. You can see as the knife moves across the beam, the amount of light that hits the detector decreases exponentially, and then from this information we can figure out what the actual beam size is and what its location is by taking the data from both measurement points.